Hello, everybody. My name is Dmitry Levin, and the name of my colleague is Eugene Syromiatnikov. And today we will talk about Strace from the point of view why would you still want to use Strace nowadays in 2023 when so many different ways of tracing on the kernel side is available. Like Strace is an oldest, I think the oldest Linux system call tracer. It appeared around the same time when the Linux kernel appeared. So why would you still want to use a tool that old, right? But why would you still use a Linux kernel which is around the same age and also about the same? Why would you? Because they evolve. And apparently, there are quite a few cases when a Strace would be the most useful. And here we will talk about those cases. So, Strace uses ptrace API, right? It's the only general purpose tracer of its kind that uses ptrace API. There are debuggers, there are some very specialized tracers, but the Strace is the only one of that kind. Therefore, it's unprivileged, unlike most other modern tools. So in some cases, actually, you don't have a choice. Like, if you own your virtual machine, and this is not an issue, but in some environments, you don't really have a choice but to use ptrace API. And also, Strace is a user space tool, right? So it can obtain a lot of data that's not that easy obtainable from the kernel, or not safe to obtain, or not secure to obtain. And for this reason, Strace can do some really complex manipulations on the user space data, on the file system data, and so on. Strace is actually the best system call decoder. I mean, it knows a lot about system calls. More than any other tracer, and this situation is not likely to change. It sounds strange because on the kernel side, kernel already knows everything, right? It actually executes all these system calls. So in theory, it could have done all this, but because the kernel is not a single piece of code, it consists of so many different drivers. For example, iOCTL implementations, they are implemented by so many different people, and they located in some different parts of the kernel code. So what happens in reality is, on the kernel side, it's much harder to decode system calls that deeply as Strace can do. Also, Strace can print a lot of information associated with file descriptors, process IDs, thread IDs, and so on. And also, Strace is not just a tracer. Some time ago, a system called tampering was implemented, which means that Strace, along with tracing, can do tampering of system calls. So, as Strace uses ptrace API, it means that it should have to be slow, right? It used to be the case before, but nowadays, the answer is it depends. So there is a huge optimization implemented in Strace that allows to minimize this overhead. By attaching an automatically generated BPF program to a system call filtering, it allows to minimize the penalty to just the penalty that's always there when SICOM filtering is used. And nowadays, it's essentially everywhere. Like systemd would most likely apply some SICOM filtering anyway. So you probably won't see any difference. So in that very famous, I would rather say infamous DD example, then you're tracing a command that issues a lot of system calls, but doesn't actually trace anything. The example was constructed by a person to demonstrate how slow a Strace is. So we can see that in a regular case scenario, a Strace would really be very slow. Like in this extreme example, it would be like 40, 50 times slower, right? 2 orders of magnitude. And with using of SICOM BPF, you wouldn't see any difference. But there are obviously some limitations. The limitations are consequences of the kernel interface that's being used to implement this. Because we can attach SICOM programs but can't detach them at all. There are situations when you can't actually attach, because when you're attaching a Strace to a already running process, you wouldn't be able to uninstall a SICOM program if you install it. For this reason, in all those cases when a Strace detaches from the traces, this option couldn't be used. I mean, you could use it, but a Strace understands, and because it's just an optimization, Strace wouldn't apply this option to those processes that it shouldn't be. And if you, by some means, would manage to terminate a Strace prematurely, currently this would result that because of the SICOM API being used, you end up with a situation when the tracee wouldn't be handled properly. I mean, those system calls that were traced before would be just failed, and this would likely terminate the program at all. So to use this option effectively, you have to filter system calls and just trace those you need. And for this, we have a lot of, just a quick recap of those interface we have, just to specify what kind of syscalls are to be traced. You can use system call names. Of course, because system call names change, and from time to time, kernel adds new system call names, and new system calls, and they have new names. And on architectures, system call names sometimes differ. So for this reason, classes of system calls were created and are being added nowadays, so that you could specify classes and don't think of these particular differences. Also, you can use regex to specify the system calls you want to filter. This really helps, especially in conjunction with the SICOM BPF optimization. So about decoders, which are the main part of a Strace, and the reason why people will be using a Strace when they really need to obtain a lot of data. For example, with ioctls, which essentially a multiplexing system call, because behind a particular subsystem, the data that goes through the system call is very different. We have support, I mean, really detailed decoding for a lot of this, for a lot of ioctl classes. This list you can see is not the full list. It's just those that are easy to recollect. And here are a few examples. For example, this is decoding of DM subsystem ioctl. It's just a simple command, and you can see how complex these structures could be. They're actually more complex. You don't see that inside they are really strange. For example, there are inside some addresses are implemented as offsets, so they're really complex. And sometimes, for example, in case of KBD subsystem, the decoder is so detailed that it is used to test the reference implementation of KBD subsystem. It's a relatively recent addition. So this way, you can actually use a Strace not just to debug things, but you can use it as a reliable way to test, to do regression testing, and use it in CI, like in this case. Also, we have a lot of netlink protocol decoders, and they are very sophisticated. If we take Alcatel decoders and netlink decoders, I think they take more than half of all Strace code base. So in this very simple example, I created a container without a network. I mean, with just a local network, just loopback and nothing more. So the routing table looks as simple as this. And if you trace this command, you will see the actual netlink protocol, the netlink route protocol. I did some coloring, so you would see exactly the same 3 lines of answer for IPv4, right? There are also, I mean, for that simple command, there are also IPv6. It just doesn't fit the slide. Sorry, it would be huge. But you get the idea that these protocols are complex, and if you need to debug them this way, Strace is probably the only way. So, as I said, Strace can do a lot of user space stuff, and this is an example. Like, Strace can be used to print execution stack trace on the user space part of the trace it processes after each trace system call or signal. So here you can see, like, when cat utility finishes its execution, it closes its std_out, and from this output you can see why. From this trace you can see that there is an exit handler, and on exit handler it just closes this std_out. Why does it do this? Because it has to return a non-zero exit code, then it fails to flush the output, so that cat would be used reliably. And here is an example with signals. Like, why would timeout receive a signal? From the stack trace you can see that actually it has a signal handler, and from this signal handler it sends this signal to itself so that it would look like it was signaled and killed by this signal. So Strace also can be used to print very detailed information associated with file descriptors and process IDs. And here, in case of file descriptors, it can print paths associated with file descriptors. It can print network information associated with sockets. It can print, of course, device numbers associated with devices, PIDs with PIDFD file descriptors, and recent addition, it can print signal mask of signal FD descriptors. So here is an example of the network information it can print. This is just a very simple netcat invocation. And you can see that first it creates a TCP socket. First it's still without an address, and then after connect system call, Strace prints more information, actual connection, right? Up to the socket closure. And also you can see here the device number. So with signal FD, which is a recent feature, you can see the signal mask and how it changes after system calls. With process IDs, Strace can print command names. It can also print information about process IDs, thread IDs, session IDs when the tracee runs in a different namespace. For example, here, when Strace prints command name, it can print it associated with process ID of a running process, and also for process IDs that are used as arguments in various places. like arguments of system calls or information supplied with SIG infrastructures that arrive with signals, as long as it's still there. For example, in the last case, when the wait for system call is invoked, in the beginning there is still a sleep process, so it prints the name. And after the wait, there is no more sleep, so just the PID file, PID number. Sorry. And so it can do the PID namespace translation, which is useful nowadays because of proliferation of containers. So in this example, you can see how the PID numbers in the created PID namespace are translated, which is really nice. And Strace can also print information about C Linux context. This is information that associated with PID numbers, with device, with file names, and with file descriptors. It can print either in short form or in a long form. It also can print mismatch if it happens. For example, in this artificial example, you can see that context actually mismatches the database ones. And the idea is that you can combine second text printing with -z option, which is quite useful. And I would like to ask Eugene to continue and talk about this mysterious -z option.
Yeah, and I'm forced to talk about it because Dmitry thinks it's funny that I was particularly salty that it's not related to C Linux at all, but rather to filtering of syscall status. So there was existing for quite some time, not -Z, but -Z option that filters only successful syscalls, but it was broken as such. It wasn't documented. So it was finally fixed in version 5.2 in 2019 before the implementation of the seccomp information providing, but minus the -Z was also taken by the filtering of the failed syscalls. And you can see in this example how it can be used. So if you run cut with -Z, you just see only successful syscalls, and with -Z only all the craft that LD provides when it tries to load all the libraries. Another filtering capability that doesn't relate to filtering on particular syscalls directly is traceofds. It allows filtering not on syscalls but file descriptors. It's complementary to path tracing capabilities that Strace also has. And for example, when you have cases when you know the file descriptor that is used for a particular purpose and it's constantly open and closed and you can't get a handle of particular paths it uses, but you can get the idea of its ID, you can just now trace on it now. As it was mentioned, Strace not... do you have a question? Yes?
Yeah, just when filtering on FDs, can we also filter on FDs that Strace actually discovered? Say we open a socket, would we be able to filter on the file descriptor opened by the socket?
Can you repeat the question?
Can you...
can we only trace, can we only specify file descriptors at execution, or would we at runtime be able to say we open a file descriptor?
Okay, I see. So the question is whether the file descriptor being traced have to be set during execution time, or they can be also traced during runtime. Yes, they can be traced during runtime because it's just ID, and Strace checks every matching syscalls that potentially can has this file descriptor ID, and if it matches, it prints it's in the output. So yes, that's to your question is yes. As I said, there is not only tracing, there is some tampering capabilities. They're mostly used for they are mostly implemented with the aim of performing various kind of testing. For example, fault injection when you force to fail various system calls, and this allows for testing of some code paths that not usually tested because, well, when you assume that everything goes fine. Actually, implementation of this feature by the student during Google Summer of Code project allows him unearthing a bug in Python, and during merge, Dmitry also unearthed a bug in LD that didn't properly handle setting of the map flags. Well, but you can also not only inject errors, but also successes, which allows you avoid executing some system calls like unlink, which allows you get access to files, to some ephemeral files created during executions of some programs and scripts. So not only we can inject like syscalls, but we can also delay them if Strace is not too slow for your particular taste, or we can just mess with it with the traces memory, but it's, well, pretty minimalistic as of now, so it just allows rewriting memory that is pointed by syscall arguments on entering or on exiting. And well, since we are constantly adding features, probably not everyone keeps track of them, and we decided at some point that it's probably a good idea to like be modern in this regard as well and provide some tips, tricks, and tweaks to users. So this option has also been implemented that provides you a random tip, trick, or tweak also after each Strace session. And there is, for example, a particular tips that suggests that medicinal effects of Strace can be achieved by invoking it with the following options, which can raise some questions like, what is it? And the answer to this is, well, a long-standing bug, which asked us to document how to just get the medicinal effects of Strace when you run a particular program under Strace, then it suddenly magically starts working. And we couldn't address this ask for quite some time, but well, with the addition of this new feature, we finally can. And this bug is finally closed as finished. And this completes our presentation. Thank you very much for attending it. And if you have some questions, I can answer to them. Yes?
I'm sorry. Who has the microphone? Because we need it if you want to be heard in the stream.
Hello. Yeah, to trace hierarchicals, how do you do the mapping? Because hierarchical numbers are unfortunately not unique. You figure out what was opened in order to get the right namespace for the hierarchicals, or how do you do it?
Yes, in order to figure out, well, in order to do PID namespace translation, Strace has to do PID namespace translation. That is, go into the procfs, go through all of the PIDs. Well, in some cases when there's difference between the mounted procfs and namespace Strace in, but otherwise you can just go to the processes proc entry, get the idea of its namespace, then find the namespace for the target PID. Then find the And to do this for all the traces and figure out what is the PID mapping for each namespace ID.
I was talking about IOCTLs, not PID mappings.
Was the question about IOCTL numbers?
Yes.
Okay, so there is...
They are not unique. So do you try?
So they are, from one side, they are not unique, but the collisions between subsystems are relatively rare, and for this reason we can distinguish them. We can actually peek into the real, how do you say, subsystem. You can actually find out what subsystem it is.
Ah, okay. From the file?
Yes.
Okay.
From the proxy file system, you can tell. No? From...
Is the discerning between USTLs in case of collision is done based on the character or the block device ID that is parameter of an EOCTL. And does anyone have any other questions? Okay, so this is it. Thank you very much.